Alright, so the topic I'd like to talk about today is second derivatives. So we've defined the derivative f prime of x, and we've said that this is also a function. In other words, we can plug in the value of x, we get some output. And so, since this is itself a function, we can forget for the moment that we got it from a derivative and just think about this as a new function, and we can find the derivative of that new function. And this is what's known as the second derivative of the function. So we denote this with f double prime of x, and this is equal to the limit as h goes to 0, f prime of x plus h minus f prime of x, all divided by h. So this is exactly the same form as the first derivative, right? Except instead of having f here, we have f prime, because we're taking the derivative of the derivative. And other notation for the second derivative, if we want to use the Leibniz notation, we would write d squared f by dx squared. And similarly, we can have the third derivative, which we would write f triple prime. We could have a fourth derivative, which we write as f with a 4 in parentheses, just because it gets tedious to write a ton of primes once this power starts getting higher. And so similarly, we could have fifth derivative and so on. Or if we wanted to write these things in Leibniz notation, you would write d cubed f by dx cubed, d4f by dx4, and so on. So the point is, every time we take the derivative, we get a new function, and we could try taking its derivative as well. So just as a quick example, if f of x is equal to x squared, we saw previously that f prime of x is equal to 2x. And then we had a rule for finding the derivative of a linear function. The derivative is just equal to the slope. So if we take the derivative of f prime, which is 2x, then we'll get the second derivative, which is 2. And then similarly, we could take the derivative of 2, and since it's a constant, we get the f triple prime is 0, and then once we reach 0, all the further derivatives will also be 0, so I won't write any more down. So this is the idea of the second derivative, and just like with the first derivative, this can tell us some information about the graph of a function. So if f double prime is greater than 0, then this tells us the derivative of f prime is positive, so that means f prime is increasing. That's something we already knew from previous work. And this also says the original function is what we call concave up. So I'll explain what that means in a moment. We can also have f double prime be negative. In this case, f prime is decreasing, and f is concave down. So what do I mean by concave up or concave down? So a concave up function is a function which is sort of curving upwards, like this one. And a concave down function is one which is sort of curving downwards like this. And so what I'd like to point out is that if we look at the tangent lines to this function, here we have some negative slope. As we get closer to 0, the slopes of the tangent lines become less negative. Then say we're at a point over here, now the slope of the tangent line is positive, and the point up here, slope of the tangent line is even more positive. So for a concave up function, the slopes of the tangent lines are increasing as we move left from right, which makes sense with this idea that f prime is increasing, as f prime is the slope of the tangent line. Similarly, for a concave down function, the slopes of the tangent lines will be decreasing as we move from left to right. So this gives us a way to interpret what the second derivative tells us about the function. It's somehow how it's curving. Is it curving upwards? So the second derivative is representing a rate of change of a rate of change. So sometimes we can interpret that as an instantaneous acceleration. So if d of t is a function representing the position of an object, then d prime of t was equal to the instantaneous velocity of that object, and d double prime is what we call the instantaneous acceleration. So it tells you how quickly the velocity was changing at that moment. So as an example, let's suppose we have some graph here. Let's draw something like this. So when we're over to the left of 0, the function is concave down. Concave up, right? It's curving upwards. And this means that the derivative is increasing. So over here we could say the function is increasing, and it's also increasing at an increasing rate, or accelerating. Over here to the right of 0, the function is concave down. So it's curving downwards. And so that means that the function values are still going up, right? The function is increasing, but now it's increasing at a decreasing rate. It's slowing down, or decelerating. So in this way, if we know information about the first and second derivatives, we can say something about how the graph looks. So for example, if we're told that to the left of 0, the function is has a positive first derivative, and it has a positive second derivative, then we could guess that the function looks something like this. And over here, it has still a positive first derivative and a negative second derivative. So we could predict that the function will look something like this, even if we hadn't already known what the graph was. And so this gives us a lot more information about what the graph will look like than just knowing the first derivative of the function. And we'll see throughout the course that the first and second derivatives are both very useful in determining information about how a function is behaving.